the explanation. All right, so we have, trying to get myself back into the swing of it. All right, so that was a situation there where we had two fixed ends. So let's take a look at the math. I'll save the demonstrations for Monday, where we actually put some of this stuff to the test. Oh, somebody was just taking a picture and I just erased it. Okay, my imagination. So the way I would represent the first harmonic is like this. This is two fixed ends. We have a node, an antinode. So when doing the analysis, one of the questions is, what does a full wave look like? Is this a full wave? Well, it's not. A full wave, if those of you who have trig, you've seen the sine curve, cosine curves, you start at some point and you go till you get back to the same point. So a cosine curve would look like that. A sine curve would, that's a sine. So a sine curve would look like that. Cosine curve would look like that. It's when you get back to the same position where I can just take this and start repeating it. If this were a standing wave, that would look like this. This is a full wave. Therefore, that is a half of a wave. So if the distance from here to here is L, then L is equal to 1/2 of a wave. Half the wavelength. This is the first harmonic. So the wavelength is equal to 2 times the length. If I wanted to figure out the frequency or the speed, I need to bring in that other relationship we'd already talked about, the fact that the speed is equal to the frequency times the wavelength. So if I'm talking the first harmonic, I know the wavelength is equal to 2 times L. So I've substituted one, I guess I know what L is. That hasn't really helped us a lot. I need some other relationship here in order to be able to do anything with it, really. Speed of a wave. We talked about how tension is a factor in the speed of a wave. The other factor in a speed of a wave is what's the actual medium that you're going through, which generally is symbolized or is taken into account by, as I move one particle, what influence will it have on the next particle? That which is part tension and part how close is the next particle. So generically, if I'm looking at the speed of a wave, it's going to be the square root of some force term divided by some inertial term. So how much force is one particle exerting on the next, and how much mass are we actually trying to move? It slows it down if I got more mass. In this case right here, I've got a very long coil or a long string, something where the thickness of it is small, tiny compared to the length of it. This is the square root of the tension divided by the linear density. This is a mu, same symbol as we use for coefficient of friction. Linear density. So, how do you find linear density? How do you find density? If I'm talking about surface density,
I have no idea.
well, mass divided by, if it's a surface, you're talking about an area, so that's mass divided by area. Linear density?
Mass divided by length.
Yep. So if I know the linear density, I can figure out, and I know the length, I can figure out frequency. Let's just do a quick plug and chug, something actually related to the lab that we won't actually do. Here it is. I have a long piece of string. The mass is 0.6 grams. The length of this piece of string is 3 meters long. I then take that string and I attach it to a string vibrator. And to the end of that string, I attach a mass. And let's figure out what that mass needs to be. The distance from here to here, so from where it's attached to the string vibrator to the top of the pulley, will make 1.2 meters. I'm assuming that this mass is going to be significantly larger than the mass of the string, and so in this down here, I'm not going to worry about the mass of the string in terms of doing calculations. As in, I'm not taking that into account in the tension. String vibrator, it's typically, if I just use the plain old one without the adapter, plug it into our outlets, it's gonna have the same frequency as our current. Anyone know what the frequency of the electricity in US is?
Is it 120?
Was that?
Is it 120?
No, that's voltage. That's an amplitude. 60 hertz. So my frequency is 60 hertz. And assume we're on Earth. All right, what is the mass required to do this? All right, so I'm over there. I'm looking at my equation over there. I'm going to get the first harmonic. Sorry, I should be more specific. What is the mass required in order to get the first harmonic? So mass to get first harmonic. I know for the first harmonic that what's going to happen here, this string, if I get it into that position, is going to look like this. This is going to be moving back and forth 60 times a second. It will look like it's in two places at once. At least for me, it looks like it's in two places at once. And it'll have nodes here and here. I have a node here because this is only, it is vibrating here, but it's vibrating very little. Here at the top of the pulley, there should be enough tension in it so that it's a node at the top of the pulley. I know that the frequency times 2L for the first harmonic is equal to the square root of the tension over the linear density. Well, I can find the linear density. I have enough information here. My linear density, M divided by L, 0.6, actually 0.0006 kilograms over 3 meters, 0.0002 kilograms per meter. L is the length from end to end, so that is 1.2 meters. Probably the biggest mistake I've seen students make is they see the 3 meters and think that's the length down here. This is the vibrating length down here. That's the length of the entire piece of string. And from a practical point of view, we're dealing with 0.6 grams. This is not an unrealistic number here. This is not much. If your balance is off, 0.2 grams, which doesn't seem like much, but if you're dealing with this level here, if you're off by 0.2 grams, you've already introduced a 33% error into the problem. So if I just did 1.2 or slightly more than 1.2 meters, this number gets even smaller, and any errors in the balance become that much more significant. And so typically, I recommend using a much longer piece of string to figuring out the linear density than you need down here. I know that down here, if this mass is in equilibrium, or close enough, that the weight of it equals the tension. And so my tension is just going to be mg. So if F squared 4F squared L squared is equal to mg over mu. M is going to be 4 times the frequency squared L squared mu divided by g. So my mass would be 4 times my frequency squared, which is 60 squared, times my length, 1.2 squared, times mu, 0.0002, divided by 9.8. And if someone would be kind enough,
.423.
0.423
Yeah.
kilograms. Anyone else get sick? Okay, got 2 people with that. You got 4.423 also? All right. So a little bit less than that. Questions here? In the traditional lab, you actually know that mass, you're trying to figure out the frequency. See how close it gets to 60. All right, the second harmonic would be the next simplest. So every time that we add a harmonic, and this is going to be true regardless of whether it's 2 fixed ends, 2 free ends, or 1 fixed, 1 free, we are going to be adding half a wave every time. So this is half of a wave. The second harmonic. It should be symmetrical, despite the way that I drew it. The spot in the middle should be a node. So I have 3 nodes now. The length is now a full wave. That's the second harmonic. The next harmonic. And they should each be the same size, despite the fact that I didn't necessarily draw it that way. So the length is equal to 1.5 waves, or the wavelength is 2/3 the length, which makes sense. If a wave is basically going from node to the second node, or if that is a full wave, that's 2/3 of the whole thing. And so on. Sometimes I see formulas for this stuff, which I don't never really care for. Because there's basically 3 different formulas, and remembering which one goes with which situation, to me, it's just easier to start here and then notice the pattern. Questions? I do want to point out that if I have a fixed in, I'm going to have a node there. I have nodes at fixed ends. Which leads into our next one fixed, one free. So if I have one fixed in, one free end. A fixed in is a node. A free end, the one who want to take a wild shot at it. So the simplest version would basically look kind of like that. Let's see if I can draw that better. Probably not, but I'm going to pretend. So we have an anti-node at the bottom. This length here is L. Node at the fixed end, anti-node at the free end. How many waves is that?
Quarter.
Yeah. So now my length is a quarter of a wave. Or the wavelength is 4 times the length. The next harmonic, well, I add a half wave every time. So the next harmonic looks something like that. So how many wavelengths is that? In unison would be really nice at the moment.
2 by 2.
How many wavelengths?
1.5.
That's not a half.
3/4?
Yeah, it's 3/4. I start with a quarter and I add a half, I get 3/4. So that's 3/4 of a wavelength. Now, when I said before, when I said the next harmonic, this actually is not the second harmonic. This is the third harmonic. Not unrelated to the fact that it's 3 times what that one was. So when I have one fixed, one free in, there is no second harmonic. This is the third harmonic. Some of the older stuff for a couple of years, I would call it the second harmonic, because it's the next one. That was a mistake, so if you're looking at, potentially in the older tests, I don't have any videos from back then, so I don't think, I hope not. But it is the third harmonic. Now some books will get around that, instead of calling it the third harmonic, they'll just call it the first overtone. The next one would be the second overtone, as opposed to first harmonic, third harmonic, fifth harmonic, and so on. There's the fifth harmonic. So now I have a full wave plus a quarter, so. So L is equal to 5/4. So and I keep adding a half every single time. So the wavelength would be 4/5 of L. In the lab room, did you see there's the tall skinny tubes that are about, I guess about yay tall, about this big around? Okay, I'm guessing you haven't seen it or are just being shy. We're going to demonstrate that on Monday, this.
Is that a 4/5 on the bottom?
Yeah, that's at 4/5. And obviously we have one left. 2 free ends. If I have 2 free ends, well, those are antinodes at the ends.
Antennas?
Yep. The simplest one I can do is this. Make that distance end to end L. What exactly is, how many waves is that?
Half.
Yeah, it's half of a wave. The next simplest. Not drawn particularly well. Only mildly better. How many waves is this?
1.
Because I had to add a half every time. The mathematics of this is the same as for the 2 fixed ends. Again, there's supposed to be some symmetry there. How many waves is this? I think you said 1.5.
Yeah.
That's all. That one we can actually demonstrate. See if I can grab that prop quickly.